Newton's three laws of motion and his law of universal gravitation provided a mechanical model that dominated scientific attitudes for 2 centuries. In the 19th century, the Scottish physicist James Clerk Maxwell developed new concepts for electromagnetism that were to challenge the Newtonian model. But because the 2 theories were successful in their own very different domains, any possibility of a confrontation seemed remote indeed. Toward the end of that century, Albert Einstein recognized the inevitability of a conflict. He devised what has become known as a thought experiment. In thought experiments, the power of imagination overcomes the limitations of experimental techniques and allows us to test theories at their extreme limits. Let's enter the world of his imagination. By applying the ordinary concepts of mechanics, he brought to light a conflict between Newton and Maxwell. It follows from first principles. You see, according to Newton, it's possible to catch up with any uniformly moving object, after which there will be no relative motion. As far as they are concerned, each will judge the other's speed to be 0. To get away, just accelerate. But in theory, the bicycle can catch up again, because according to Newton, there is no upper limit to speeds. That is, in theory. Einstein applied this sort of reasoning to the relative motion of light. Suppose that instead of the boat, the uniformly moving object was light, pulses of light. According to Newton, we should be able to catch up with it, after which its relative speed will be 0, just like the bicycle and the boat. Not so, according to Maxwell. The speed of light is absolute, invariable. There is our confrontation between Newton and Maxwell. Which of the 2 theories is wrong? What we mean by wrong here is that the theory does not hold up when pushed far outside its original domain, where it still works admirably. We have already suggested that Newtonian mechanics is on shaky ground because of the finiteness and absoluteness of the speed of light, as predicted by Maxwell. But how reliable is Maxwell? Perhaps the very large magnitude of c compared to ordinary mechanical speeds could conceal the Newtonian nature of light. Then, a very rapidly moving light source could throw off light with a significantly increased speed, just as a bullet fired straight ahead from a moving car has its speed increased by the speed of the car. Does light behave in this way? If so, the foundations of Newtonian mechanics might yet be secure.
Newton would have been the first to agree that the only way to settle an issue like this is by doing an experiment. But what kind of experiment? Well, if we think about the gun in the moving car, then a bullet fired out in the forward direction would be faster than normal by the amount equal to the speed of the car. And similarly, if you fired out a bullet to the rear, that would be going slower. So what we would like is a situation where you have a moving source of light, and we could compare the speed of the light going out in the forward direction compared to that at the rear. Well, it was way back in 1913 that the astronomer De Sitter pointed out that nature had already set up such an experiment and provided us with an answer. Out in space, there are binary stars, two stars close to each other and going round each other. Suppose we have two stars like these. We're on the Earth observing the light from them. Each time the fainter star passes this point in its orbit, the light it emits in the backward direction towards the Earth is expected to be traveling slower than normal. It will have the normal speed of light minus the speed of the star itself. When it passes this other point on the opposite side, the speed of the source is added, so that light is faster than normal. Now, if this is how light actually behaves, some interesting effects should be observed. For example, it would be possible to have a situation where the speed of the star and the distance to the Earth were such that a slow pulse emitted from here would arrive at the Earth at the same time as the fast pulse emitted half a revolution period later. This would mean that the faint star would be seen at both positions at the same time. Now that, of course, would be a very special situation to see double images on exactly opposite sides of the orbit. But in general, there would be multiple images and spread out images if the speed of light really did depend on the speed of the source. But as De Sitter pointed out, the images of binary stars are perfectly well behaved. Now, this is such a fundamental result that physicists even today are still testing it out to ever greater precision. For example, there was a worry that perhaps somehow the interstellar gas between us and the binary star system might be affecting the observation. After all, it's known that when light passes through air, it tends to slow down a bit compared to its speed in a vacuum. And, well, the way to get around that problem is to use a different form of electromagnetic radiation, X-rays, which one knows are hardly affected at all by their passage through air. So in 1977, the same experiment was repeated again, but this time using binary stars emitting X-rays. But the result was the same. There was still absolutely no effect, no double images, and no smearing out. And this experiment was done to a precision which was 5 orders of magnitude greater than that of De Sitter. And so now the present situation is that we can say that if there is a tendency for the speed of the source to add part of its motion onto that of light, then the fraction added cannot be greater than 2 parts in 1,000 million. So it's pretty certain that we can say that the speed of light is certainly not affected by the speed of the source.
So Maxwell is right, at least in that the speed of light is not affected by the motion of the light source, as Newton would have had it. Now, how do we stand with the Einstein thought experiment? There, a light source, the lamp, emits pulses of light, and a spaceship sets out to catch them. Suppose that after the spaceship has gotten up to a decent speed, the spacemen look back at the lamp. They see it rapidly receding, a moving source of light. But we now know experimentally that the motion of the source has no effect on the speed of light. Their efforts to catch the light have been in vain. They can never travel as fast as light. But wait. Implicit in that argument is the fundamental idea of Newtonian mechanics that only relative motion counts. It takes for granted that whether the lamp is at rest and the spaceship moving, or the spaceship at rest and the lamp moving, precisely the same physical situation is being described. Could it be that this concept of relativity fails for light and electromagnetism when pushed to the limit, as it certainly is in the Einstein thought experiment? Perhaps Maxwell's theory is only strictly valid in some special reference frame or coordinate system. It might be the one in which the sun is at rest, for example, and an observer in motion relative to that special coordinate system will find that the speed of light has changed. If this were so, it should be possible to exploit the variable velocity of the Earth in its orbit about the sun in a test for such an effect on the speed of light. This is the famous Michelson-Morley experiment, but before we launch into the description of that experiment and its outcome, let's explain the basis of the experiment through a simple analogy. High in the atmosphere, winds blow a great speed. They are known as jet streams. These winds have a significant effect on airplane schedules. To allow for them, we must know their speed and direction. Our story begins at Los Angeles International Airport, LAX for short. An airport dispatcher wants to get that jet stream information. He sends two planes off at the same time, one eastward to Dallas and the other northward to Calgary. These two cities are almost equally distant from LAX. The pilots are instructed to fly round trips to their respective cities at the same speed in still air. By noting which plane returns first and by what time advantage, the dispatcher can work out the speed and direction of the jet stream. To explain what he has in mind, let's suppose the jet stream is running directly to the east at a fixed speed, say 600 kilometers per hour. If the speed of the aircraft is 1,000 kilometers per hour, then its speed eastward is increased by the jet stream to 1,600 kilometers per hour. It arrives at Dallas after a certain time, which we call 1 unit. On the return trip, it's fighting the jet stream, so its speed is reduced by 600 kilometers per hour to 400 kilometers per hour, 1/4 of the speed of 1,600 kilometers per hour it had going eastward. So it takes 4 times longer, 4 units of time. It returns to LAX after a total elapsed time of 1 + 4, 5 time units. Meanwhile, the other plane was sent off between LAX and Calgary. In the eastward trip, the plane was either speeded up or slowed down by the jet stream. Now it is blown off course, and to get back on course, due north, the pilot must head into the wind. But what effect will this have on the journey time? The plane's speed in still air is 1,000 kilometers per hour, 5 units on the grid, and the jet stream blows across at 600 kilometers per hour, 3 units. To regain direction, the pilot heads into the wind. His northerly speed is reduced, but by how much? We can work that out from this right-angle triangle. It is a 3-4-5 triangle with vertical side 4 units. So the northerly speed of the airplane is 800 kilometers per hour. That is half the speed for the trip LAX to Dallas, which took 1 time unit. So this plane reaches Calgary in 2 time units. On the return trip to LAX, it must again head into the wind, and this leg also takes 2 time units. Now we see the outcome. The round trip perpendicular to the jet stream takes only 4 time units, whereas the round trip parallel to the jet stream takes 5 time units. So our airport dispatcher can use the knowledge of which was the longer trip to learn the direction of the jet stream. And from the ratio of the time units, here 5:4, he can learn the speed of the jet stream. Now remember that all this is an analogy in which the speed of the airplane in still air becomes the speed of light, and the jet stream is the motion of the Earth relative to the special reference frame. The comparison of the time for a back and forth journey in one direction with that for a perpendicular direction is the attempt to detect and measure such motion. This is the Michelson-Morley experiment. It was carried out in 1887 in Cleveland, Ohio. To perform their delicate experiment, they set up their laboratory in a cellar at the Case School of Applied Science.
Well, the idea was simple enough. They took light from a source, and it went over to this point here. And at this point, the light was split up into two beams, which were dispatched at right angles to each other, rather like those aircraft. And they went off equal distances and were then reflected back from the mirrors at the far end and came back to the same point. And from here, they then went on into the telescope where they could be viewed. And by looking down the telescope, one had to estimate the difference in the arrival times of the two beams. Now, of course, the challenge in this experiment is to measure this very, very tiny difference in the arrival times. One idea was to use not single mirrors, but sets of mirrors. This increased the distance the light had to travel by making it bounce repeatedly back and forth before going into the telescope. This, of course, increased the difference in the arrival times. But the really crucial feature was that they used the phenomenon of interference. To bring this about, they caused the two beams to become superimposed on each other on their way into the telescope. As a result, these two beams interfered with each other. What you see in the telescope is this. It's a series of light and dark bands, and you always get this kind of pattern when you take a beam of light and you split it up and make it go different paths and reunite it. Now, the problem with that pattern is that it doesn't of itself tell you how much one of the beams is lagging behind the other. But what you can do with a pattern like that is to use it to show a change in lag. Now, what I mean by that is, suppose we change the amount of lag, we get this kind of thing. You see, the whole pattern moves to one side, and the difference in the lag is measured by the amount of that shift. Michelson and Morley found that there were many different sources of shifts. Traffic going past, people walking about. That, incidentally, is why the experiment was carried out down here in a cellar, and why the apparatus is set up on this very solid sandstone block. So, using this, they were able to get rid of all these extraneous sources of shift. How could they introduce a shift, though, which would actually be useful to them? Well, they used a very ingenious idea. They looked down the telescope at the interference pattern with the apparatus like this, and then they did this. The whole thing rotates. Now, what's the idea? Well, let's suppose those are our two beams at right angles to each other, and for the sake of argument, let's say that this one is lagging behind the other. Now we do a rotation, and let's say it goes through 90 degrees, and when that happens, we've now interchanged the beams, and it's now this one which is doing the lagging. So the rotation introduces a change in the lag, and that should show itself up in the telescope by seeing the interference pattern move bodily over to one side. And by measuring the amount of that shift, that will tell us the size of the lag. So what did Michelson and Morley find? Nothing. Absolutely nothing. During the rotation, the pattern just stayed completely stationary. And the only way to explain that is by saying that the arrival times of the two beams are identical, that one does not lag behind the other. In other words, that the motion of the Earth around the Sun in no way affects the speed of light. And this experiment has now been repeated in a modern version using a laser rather than this source. And the modern version has shown that the effect that Michelson and Morley were looking for is not there to less than 1 part in 1,000.
And there we have it. There is no special reference frame where the behavior of light is somehow simpler than in any other frame. The principle of relativity does apply to the motion of light. But we have seen in this program how different light is compared with the objects of ordinary experience. The speed of light is an absolute barrier. Not only can it never be crossed, it can never even be attained by a material body. Perhaps you're saying this is all too strange, too bizarre to be true. But it's the real world we've been talking about. If these things seem strange, it's because you are reacting to them with the conditioning that our limited earthbound experience has given us, as set down in the Newtonian concepts of space and time. It is not the phenomena that are wrong, it is the Newtonian space-time concepts that are wrong when they are applied very far from the circumstances for which they were originally conceived and still admirably represent. It is just this necessary reconstruction of the concepts of space and time that Einstein did for us in 1905 when he created his special theory of relativity. And in doing so, he made use of and reconciled the two basic ideas of this program. They are the principle of relativity, that the descriptions provided by two observers in constant relative motion are equally valid. Stated more generally, the laws of physics are the same for both, and that among those laws is the absoluteness of the speed of light, that the speed of light is the same for any two observers in constant relative motion.